Okay, reaction mechanisms. It kind of reminds me of the Wizard of Oz. Near the end, Dorothy gets to see the wizard behind the, it's like, are you familiar with Wizard of Oz? Okay. And that's what kind of peeking behind what's really going on behind to create a reaction. This idea of something going on behind the reaction that we see. Okay, so reaction mechanisms are kind of a behind-the-scenes, step-by-step kind of detailed how the reaction of interest occurs, and sometimes it's broken down into these things called elementary steps. Okay, so it's what's really going on. It's called the overall reaction mechanism. It's kind of like when we turn on a light switch, we think the light gets here right away, but it really actually takes a little bit of time. It's kind of like that. I think that actually what we think just occurs just like that as a reaction, actually there's multiple things going on behind the scenes. Oops. Should everybody get that? Okay. So reaction mechanisms oftentimes are listed out by these different things going on in sequence. And these different things behind the scenes are called elementary steps. It's possible for a reaction just to occur in one step. So basically what you see is what you get. But other times there are these elementary steps that add together to make the reaction mechanism. So I was getting ready for today's lecture, and I couldn't help but smile and think of Hess's law. Remember how we said, basically, if you have a reaction of interest and you have these that you want to know it's delta H, but you have these other reactions, and you know they're delta H, you can add these up to get to that. Hess's law. And it kind of reminds me of that, in that the elementary steps add up to the reaction of interest. So with the individual elementary steps, only with the elementary steps, there's this cool thing called molecularity. It's a really helpful thing. So the molecularity of an elementary step, okay, is basically how many particles are reacting. Okay, so the molecularity only looks at the reactants. And actually molecularity is going to be unimolecular, 1, bimolecular, 2, and termolecular, 3. How many particles are reacting on the reactant side of an elementary step? Okay, I'm gonna emphasize that, because this is where I sometimes, when students go to doing other things in this course, we want to apply molecularity. We want to apply this molecularity, this unimolecular, bimolecular, termolecular. We want to apply that to just a regular reaction. You cannot. Okay. All right. So unimolecular, I'm going to show you some examples, but basically it's an elementary step that only has one reactant, one participating particle. Bimolecular, 2, like a bicycle, 2 particles. And then the last one we're going to concern ourselves with is you'll hear me call it termolecular or trimolecular. It's the same thing, ter or tri. And it means that there's 3 particles, but I'm going to try to convince you that the odds of having an elementary step where really 3 particles need to successfully find each other and proceed to form products, that's not generally the way life is. That's just very unlikely. All right, so these could be potentially elementary steps. A goes to form B, an elementary step. A breaks apart to form B and C, an elementary step. Notice both of those are unimolecular because there's only one little particle in the elementary step on the reactant side. Some examples of bimolecular steps. These are all bimolecular because you have 2 particles. Now, to me, I guess I would argue that elementary step number 2 and 3 are basically the same thing. A plus A going to form B, 2A going to form B. Bimolecular. So example of a termolecular would be this, just kind of generic, right? Just randomly. We have 3 particles, 1 particle is A and 2 particles are B. And if this is an elementary step, then it's termolecular or trimolecular elementary step. But do you see where the odds are of those 3 particles coming together? It just gets pretty chancy. So I'm going to kind of tell you that most trimolecular actually, behind the scenes, are doing something other than, it's probably not a correct elementary step. Do you see where if we take the overall, if it's a reaction of interest, okay, not an elementary step, A plus 2B goes to form C, we could break it down into these 2 elementary steps. We take 2B to form something called D now, right? And you're like, D isn't even up there. We're going to talk about how their elementary steps often make these like invisible products that they are, I can't remember the word for it, but they are intermediates. They form these intermediates that actually don't show up in the overall reaction of interest. D is then consumed by reacting with A, okay, to form C, which if I were to draw a line, let's just go ahead and do that, just like we did with Hess's law. We're going to be adding equations. So remember how this works. I could draw a line here. I could cancel things that cancel. My D's cancel. Actually, that's an intermediate. And I bring down what's left. A plus 2B goes to form C, okay, which is this, okay? But as I'm saying down here, I'm actually breaking it down into 2 elementary steps. Okay, so that's kind of what we're up against. So termolecular, I don't know. All right, this actually is one of the themes for Unit 2. We said that those rate law expressions, rate equations, rate law expressions, it's the same thing, that rate is equal to K times, A raised to the M times B, molar concentration of B raised to the N. We said that we have to do experimentation to get those. There's an assortment of ways you get to your reaction orders. We have different possibilities that we talked about earlier. But you can't get it from the stoichiometry. If what somebody has written down or told you they know for sure is an elementary step, you can get the rate law expression for that elementary step from the molecularity of that elementary step. If it's an elementary step. Okay, this is where, like I said, I'm trying to emphasize this because sometimes we'll switch gears and like, oh yeah, the stoichiometric coefficient, that's its molecularity. Or that's its reaction order, that's its reaction order. No. Okay. Let me show you what I mean by this. So, if somebody says this is an elementary step, A rearranges to form B, then the rate law expression for this elementary step, I should say it this way, the reaction order of A is 1. So the rate law expression for that elementary step is basically K times the molar concentration of A raised to the first power because it's its molecularity. That's its stoichiometric coefficient. Okay? Because it's an elementary step. Bimolecular, okay? We know that rate should be equal to K times the molar concentration of A raised to its reaction order times the molar concentration of B raised to its reaction order. In this case, they're both 1 because it's an elementary step. The rate for that elementary step is equal to K times the molar concentration of A raised to the first power times the molar concentration of B raised to the first power because it's an elementary step. Okay, let's look at another one. One more. What if we have another bimolecular elementary step. 2 particles of A find each other, which is quite possible, to go to form product B. In this case, what is the reaction order of A? It's going to be 2. Because it's an elementary step. come up with the rate law expression for that elementary step. Rate is equal to K times the molar concentration of A raised to the second power, this reaction order. When we get going here, I'm going to go ahead and I'm just going to number these. Like if this is an elementary step 1, this is an elementary step 2, this is an elementary step 3. Okay, they're probably different reactions because they don't really look like they're adding up to be anything of interest down at the bottom there. Maybe they would. But I want to emphasize this because actually the rate of elementary step 1 is equal to the rate law constant K1 times the molar concentration of A. For the second one, we have a different rate. For that second elementary step, it'll have a different rate law constant K. Okay? And for the third one, again, it will have a different rate and a different rate law constant. All right. So this is fun too. Have you ever, I don't know how big your families are, like if you came from a family of 3 or 4, hold up your fingers. How many was in your family, including your parent or parents? So ahead. Whoa.
Well, it depends. Most of my siblings.
Whoa,
moved
6
out when I was
back there?
born.
Oh, okay, so growing up you were kind of a
Yeah, so.
threesome? Okay. Well, whether it's this or whether it's this, okay, was there ever somebody who just like was slowest to get out of the house? If you're all going somewhere? Okay. So basically that slow person was the person who decided if you got there on time or not. That was the slow one was the person who basically dictated kind of what time you made it to where you were trying to get to. It's the similar thing with if you have a number of things that need to happen, a number of elementary steps going on, there's a good chance that one of them is the slow one. And it's the time or the rate of that slow one that basically drives the overall rate of getting things done, the overall rate of your reaction. That's called the rate determining step, the rate determining elementary step. And it's the slowest. But we still love them, right? So when we get going here, you're going to see basically mechanisms that have 2 steps or mechanisms that have 3 elementary steps. And it's going to be important that one of them will be slow. The others will be fast. And it's the slow one, it's the rate of the slow one that actually is going to translate into what you observe as the rate of the reaction. Getting out the door. All right. So there's a couple of possibilities. If you have multiple elementary steps going on, behind the scenes, if your slowest one is the first one, then kind of think of it as this. It goes slow, fast, 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 fast. Okay. The other scenario, just in general, is if your last one is slow, think of it as going fast, 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 slow, and then it finishes, okay? So that's kind of what's going on. That's how that works. It will kind of pause when it gets to the slow step. And it's that pause, actually, that is what we're going to observe as the overall observed rate law expression. So we already saw an example. D a little bit ago was an intermediate. Remember, D actually, when we were talking about a termolecular actually being as two separate elementary steps, more likely the D formed was gobbled up in the second elementary step, and it never really showed basically up in an overall reaction. So, reaction intermediate. I see species, I always want to think like something like an alien species or something, like, it's a little different something, species in chemistry. So reaction intermediates should cancel each other out in your overall, in your scheme of things, how you laid out your elementary steps. Okay. So the intermediate will not appear at the bottom if you're kind of adding them up like we normally kind of add up, line up things to be added up and total them at the bottom. It won't appear at the bottom, okay? Sometimes they can be isolatable, which means you can snag them before they're consumed, okay? Or sometimes they can't be. They're just fleeting in the night. Okay, so when you come up with a set of elementary steps to overall explain a reaction of interest, then your list of elementary steps needs to make sense for what you observe with regard to adding or subtracting products, your overall rate law expression. Okay, we're going to talk about what catalysts are here in a minute. Inhibitors or catalysts are kind of opposite of each other. All right. So, a mechanism, it's possible that you peek behind the curtain and all it is there is just one elementary step. Okay? And actually we call that, I think the word is an elementary mechanism, meaning behind the scenes there's only one elementary step. It's possible. Okay? A reaction whose mechanism consists only of one step. So if you're like, I never thought about this until now, but like if you're one person trying to get out the door, then who is it that makes you get there on time or not? It's that one person. So you are the rate determining step. Okay. So somebody told us that actually this particular reaction, okay, occurs in one step. They have to tell you that because to me, you know, when we work these problems, they have to give us a little bit of information. The fact that it happens only in one step, like I said, this reaction is an elementary reaction. It only has one elementary step. So guess what? We get to use molecularity. We get to go ahead and write its rate law expression using the molar concentrations of each of the reactants raised to their stoichiometric coefficient, which is 1. We can knock out the rate law expression for this one. Okay, so let's just do that. Down there at the bottom, I'm going to say rate is equal to K times the molar concentration of N2O raised to the first power times the molar concentration of NO also raised to the first power. Why? Because it occurs in one elementary step. It's an elementary reaction. So I can use molecularity. Don't get used to it. So I have some like little pictures to kind of show that going on. I think I have too many pictures, so just bear with me. Those are the two reactants reacting to form the product ultimately. Now, this actually we're going to see an energy diagram coming up here in a minute, the same energy diagram we looked at the other day. We talked about activation energy barriers, okay? And I think I may have said at the top there can be this what we call transition state, okay? So that's the in-betweener of the reactants and the products. Here are the reactants, here are the products, the last line, and kind of the in-betweener at the top of the hill, the energy activation barrier is that thing. A lot of times, and you see the word complex, and a lot of times these kind of weird things that are kind of stuck together with weird bonds, they're called complexes. Okay? And they're shown as in brackets. Okay, so that's one way to look at it. That's the Lewis structures. Same thing, like I said, I have too many of this. The two reactants going to form products. But if we go ahead with the ball and stick and go ahead and show that transition state, it looks like this. So, again, it's an elementary reaction, occurs in only one elementary step. Don't get used to it. So this is what we looked at the other day, because we talked about activation energy barriers, which, let's pick on green. Okay, right here, right there, that's the activation energy. You see your transition state at the top, you see your reactants here and your products there. We said the change in enthalpy for the reaction in the forward direction is this right here. There's your delta H of your reaction. All right. Well, let's look at a deal where behind the scenes there are 2 elementary steps. And when we pencil this in, actually for your homework, what I'm going to try to kind of get you used to is writing step number 1, step number 2, draw a line, reaction of interest. This says actually it tells us that the initial step is slow. This is what I mean to say. Step number 1, step number 2, draw a line. This is your reaction of interest. And it's already telling us that it's an initial slow step. So next to 1, I'm going to put slow. And I'm going to put fast there. So you kind of get the idea of how problems are set up and how they give you information. So actually, just to kind of finish that thought, I am going to focus on this one as determining my rate. Determines rate. Okay. All right, so let's see the example. Okay, H2 reacting with 2ICl going to form I2 and 2HCl. That's the reaction of interest. Now it tells us that, so that would go at the bottom, right? If we were working a problem, that would go at the bottom. It goes ahead and it tells us that the observed rate was this. And so can you see where actually on the previous slide, that must be indicating, that's supposed to be the word indicating, molecularity of first elementary step. Does that make sense? Why? Because the first one's the slow one, and it drives this observed rate. Well, dang, we can go ahead and just kind of pick that up. And so does it make sense that our first elementary step should be 1 H2 plus 1 ICl? Right? I think so too. There you go. The first step is 1 H2 plus 1 ICl. Why? Because it's slow and we observed it in the rate. Now the second one, actually, we could deduce it if we needed to, but I'm going to go ahead and show it to you. We could kind of do a subtraction. Okay? I went ahead and showed it to you. But, yeah. So do you see any intermediates there? How many people see an intermediate? How many people see Mr. Snuffleupagus? An intermediate is something that you see it up here, but it's not in your overall reaction because it disappears. How many people see an intermediate? Snuffleupagus? Yeah. What is it? It is the HI. Very good. That goes away. That's your intermediate. And then can you see where you add them together? Okay. And you do get, it's like Hess's law. Doesn't it remind you of Hess's law? Okay, so it is adding up correctly. Let's see. Yeah. But do you see where, because this is an elementary step, and this goes back to what we did a little bit ago, we could come up with, let's see, rate 1, because that's the first elementary step, is equal to the molar concentration of H2 times the molar concentration, I'm running out of room, of ICl, raised to the first power, the molecularity. Check this out. Let's go ahead and do that for the second elementary step. It seems kind of strange, but check that. Maybe not. So rate 2, it goes fast, so we're not going to worry about it. That we can also use molecularity because it's an elementary step. So rate 2 is equal to molar concentration of HI times the molar concentration of ICL, both raised to the first power because that's their stoichiometric coefficient. Okay? But this one we focus on because it's slow. All right. Very good. So whatever your proposed mechanism, in this case the proposed mechanism was 2 elementary steps. The first one slow, written out. The second one fast, written out. Of course they add up to the overall reaction of interest, which is important, but the molecularity of the slow one gives us our observed rate. And that's awesome. That's kind of how you prove that you're right, which we all want to be. Okay, but only if it's an elementary step can you use molecularity to knock out those reaction orders. Okay, that's the only time. Let's look at some energy diagrams. Okay, so this would be exothermic. Check out the 2 humps. The 2 humps means that there are 2 elementary steps going on behind the scenes. Okay, it's exothermic because the energy of the products is less than the energy of the reactants, so energy is released. So in the example a little bit ago, this is where our HI is. Okay, our intermediate is hiding in here. Intermediate is not the same thing as the transition state. Transition state is at the top of the energy barrier. Okay, so those are the kind of the 2 elementary steps. Let's look at the first elementary step. Actually then, we could come up with the enthalpy of reaction for the first elementary step, and it would be right there. That's the delta H for the first elementary step. The energy barrier for the first elementary step, oh, I guess I'm not doing that one. Now let's come up with the enthalpy of reaction of the second elementary step. It's right there. Can't remember what I do next. Overall, it's that. Okay, no surprises there. Now, activation energy? Yes. Activation energy for the first elementary step is right there. Activation energy is from the reactants to the hump. Okay? So for the second elementary step, it's from the reactants, which are intermediates, to the hump. So there's the cute little activation energy of the second one, elementary step. So that's kind of an energy diagram looking at those 2 elementary steps proceeding from reactants to products, and the intermediate in between. So what I just diagrammed is this. And like I said, there is the intermediate you guys told me was there. Let's look at another one. And this one, if you want to put a star next to it, it takes it up a little bit a notch. And actually, this example is kind of like what your homework will be due that's due Monday. Seems like you need to apply this approach. All right, so let's just diagram this, all right? So like, let's see. Reaction mechanism, got that. Consists of initial slow and fast second. Okay, so 1, 2, oh, maybe this isn't what I thought it was, fast. This is what we did before, isn't it? No, this isn't what I thought. You might have to take your star back. Okay, so a different reaction. What are they telling us about it? Well, they said that they went ahead and however they did it, they got to the reaction order of the 2 reactants, NO2 and CO, when we talked earlier how they got to that via experimentation. So this is the observed rate law expression. Notice it's 0 order with regard to that second reactant. So anything raised to the 0 order is 1. So of course that goes away in our overall rate law expression. So the observed rate law expression is the rate law constant times NO2 raised to the second power. So you're all right. So that means that the rate determining the slow step, that first initial slow step, needs to somehow account for NO2 being bimolecular somehow. So this just kind of says if it did occur in one step, which it doesn't because they told us it's 2 elementary steps, then we could use molecularity and we definitely wouldn't come up with the observed rate law expression. I don't want to throw you off, but this is not what they observed it. They observed it to be second order for NO2, 0 order for CO2. It's not an elementary reaction. It doesn't occur in one elementary step. We're at that easy, right? We can't use the molecularity to get to the rate law expression. So let's look at what they propose it to occur in one slow and then followed by a fast step. Let's just say for kicks, because remember it's second order for NO2, and NO2 is our slow first step. So let's just go ahead and start out, and I think it would be hard to kind of find my way through this. But what if NO2 connects with NO2 to form an intermediate? 2 intermediates, right? NO3 and NO. That would work, right? Second order for NO2. And then what if our second elementary step takes the, NO's not intermediate, sorry. Takes the intermediate NO3 and combines it with the second reactant CO to form NO2 and CO2. So let's see how those would add up to. That actually would explain it being second order for NO2. Let's make sure that we actually add up. You guys would tell me this is an intermediate, right? So it goes away. And actually, it's not an intermediate, but one of these NO2s cancels out with one of those NO2s. Okay, and it looks like I'm ready just to bring down what I have left. But the point is that if we came up with something called rate 1, let's see if I write it under here, rate 1 being the rate of the first elementary step, okay, we would focus on the reactants, only reactant. Okay, so that would be second order with regard to, I'm going to put would be equal to K1 times the molar concentration of NO2 raised to its molecularity, which is 2. Okay, so that is what we observed. So we have just proven the fact that these 2 elementary steps, to me it's important that they add up to be equal to the reaction of interest. The fact that they equal the reaction of interest and the fact that the slow one, its molecularity is the observed rate law expression, you're like, that must be it. Pat yourselves on the back, right? Okay, so it just kind of says, so in your homework or on a test, when I say, prove that the mechanism that you're given, the set of elementary steps, prove that all things considered, what's fast or what's slow, I guess I should say what's slow, the rate determining step, elementary step, prove that it is correct. This is what I'm talking about. Notice this is the first time that, and you're going to see kind of this convention used here in a minute, but this is the first time that actually, the 1 is referring to the first elementary step, okay? And this actually, to me, there should be a 1 there. The rate for the first elementary step is equal to K1, rate law constant for that first elementary step, times the molecularity, or NO2 raised to its molecularity. So down here then, kind of, we basically say, when you look at that rate law constant and the rate, actually it's approximately equal to the rate law constant for the first elementary step. That's what it is. All right. All right, so this one might be the star one. Don't know. I've kind of lost track. Okay, initial fast and a slow second. So initial fast and the second one is slow. Usually, and let me go ahead and say what you're going to see here in a minute, I think. The ones that are fast, it will usually say fast to equilibrium. Unit 3, we're going to talk a lot about chemical equilibrium. And let me go ahead and show you what that looks like. So when it says fast to equilibrium, basically you have an arrow going that way and an arrow going this way. And then, of course, your slow one has just a normal arrow going that way. And they have to still, and we'll do an example, have to add up to be equal to your reaction of interest. Okay. So here we go. This is the reaction of interest, right? And this one actually has a kind of a cool catch. So that's the reaction of interest. And they went ahead and ran some trials and found out that actually it was second order with regard to NO, and it was first order with regard to Br2. And like, ooh, maybe it's an elementary reaction, because don't those kind of, that actually is the molecularity in the reaction of interest. Okay, 2NO, 1Br, okay. But that would mean, if that's an elementary step, and I kind of talk you through this, maybe this is the only thing I can talk you through. It's not likely to be, just in general, trust me, if you have an elementary step that requires 3 particles, in this case 2 NOs getting to form, meeting up with 1 BR, okay, that odds are not good. So I guess I'll go ahead and answer this question. Why is it not likely for it to be an elementary reaction? Because I'll say molecular, because that's how I learned it. Molecular elementary steps are unlikely. Unlikely to occur. And that would be what's required. All right. Well, if it does have elementary steps, these elementary steps actually would get you where you need to be. So instead of you, there's different types of problems, but you could be faced with a problem like this that basically says, okay, I'm proposing 2 elementary steps to give you the overall reaction of interest. Does it make sense? Is it consistent with the rate law expression where NO is second order and Br2 is first order? Does that make sense? I'm going to show you how to work this problem. I already told you we're going to focus on, does this make sense? We're going to have to focus on this one. Let's just knock out the second elementary step. Let's go ahead and write the rate law expression for that. Okay, so rate 2, since it's slow, would be equal to K2 times the molar concentration of NOBr2 raised to the first power times the molar concentration of NO raised to the first power. We can use molecularity to get to that rate determining step because it's an elementary step. The problem is, and you maybe already recognize it, is the NOBr is an intermediate. And you cannot have your rate law expression in terms of an intermediate. This has to go away. And I'm going to show you how to get that to go away. It doesn't go away, it's just substituted in for something that's not an intermediate. Okay, so this says actually we've gotten in the habit of looking at the elementary steps, focusing on the elementary steps. It's slow, using molecularity to write rate law expression, and kind of going from there. But we run into a snag because this rate law expression has an intermediate. So we can't leave it there. So the trick to getting rid of that NOBr2, which is an intermediate, is this. We turn our attention, and this will always be the case, we turn our attention to the equilibrium above it that is fast. The equilibrium above it also has that NOBr2. Okay, NOBr, NOBr2. So the fast equilibrium above it looks like this. This is the first elementary step. One of the things, like I said, unit 3 in here talks a lot about chemical equilibrium. It's wonderful. Okay, but we say it's at equilibrium, and you guys know it goes from left to right and from right back to left again. The reaction is going both directions. So it's at equilibrium if how fast it's going, the rate it's going in the forward direction is equal to the rate it's going in the reverse direction. Okay, so if we buy that, let's go ahead and write a rate law expression for the forward direction and a rate law expression for the reverse direction. The rate law expression for the forward direction would be equal to, remember we always focus on the reactants. So in the forward direction, it's the molar concentration of NO raised to the first power, because its molecularity is 1, times the molar concentration of Br2 raised to the first power. That's in the forward direction, times its rate law constant K1. Okay. Now let's look at, if we go from right back to left again, check this out. Its rate law expression would look like this. It's the rate in reverse direction. Now the reactant is NOBr2. Its molecularity is 1. Okay, so in the reverse direction, it's some rate law constant. We'll call it K minus 1 because it's going in the reverse direction, times the molar concentration of NOBr2 because that is our reactant going backwards, raised to its reaction order or molecularity. We can use molecularity since it's an elementary step, 1. Is that right? So above there, see where we say rate of the forward is equal to rate of the reverse reaction by definition? I'm going to set these two equal to each other. Okay, there you go. So K1, molar concentration of NO, molar concentration of Br2 is equal to K minus 1, molar concentration of NOBr2. And we're close. Remember, the whole reason we're doing this is to basically get rid of our NOBr2 in our slow step. So let's isolate NOBr2 by itself. Here we go. So actually, what would we do? Divide both sides by K negative 1? That would do it. So we divide both sides by K minus 1. So we got NOBr2 by itself. That's our intermediate. The thing you see under that is actually, and I'll go ahead and write on it. My writings are going to go away, but that's okay. This thing right here, this is what we got from the slow step. If you look back in your notes a little bit, that's what we got from the slow step. And this is what we're trying to get rid of, and now this is how we're going to get rid of it. We're basically going to take that quantity, you know what I mean, including the PR2. We're going to take that quantity and substitute it in there. That's it. So it looks a little funky, a little messy maybe even. Kind of bring the K's together. The K1 over K minus 1 is along for the ride. Okay, we already had a K2 there because of the rate determining step, that second elementary step. Kind of combine those. We're going to put them all into one K here in a minute. But notice we then have the NOBr2 from that and the NO from this one. Does that make sense? And of course, you probably recognize we have two NO terms, so we can go ahead and square that, combine those. Okay. So we're going to ball up all of the K's into one rate law constant, K. We're going to combine the NOs, molar concentration of NOs. We're going to square it because there's two of them. And of course, bring down the molar concentration of Br2. And does that look familiar? Okay, that was the observed rate law expression. So now using that little trick, the proposed mechanism is correct. The proposed mechanism is consistent with what's observed. Okay, so switching gears a little bit, I think. I'm going to look at another energy diagram here in a minute and look at the effect of a catalyst. So when we look at the energy diagram here in a minute, look at the effect on activation energy. Catalysts, what do? They provide an alternate, which this just blows my mind. I can't picture how catalysts work. But they provide a different mechanism. You're like, really? And by that alternative mechanism, that different mechanism, look for the humps. The energy barriers are less. Okay? And so that's significant. If the energy barrier is less, then the reaction is more likely to proceed. The cool thing about catalysts is they are not consumed. They're like reusable, which is kind of fun. Okay, so an energy diagram where a catalyst is working might look like this. So the one on the left is actually no catalyst, and the one on the right is with a catalyst. Look for the energy barrier. Doesn't this one over here look like, if they're both drawn to the same scale, less energy barrier? Yeah. An alternate pathway. In this case, they're adding hydrogen to kick it off. Notice that the second one over here, their catalyst is hydrogen, and you get your hydrogen back. It's not consumed. This is actually another type of catalyst sort of deal. Look at the difference in the activation energy required for your reactants to proceed to form products. It's the same chemical reaction, the same delta H, okay? But the blue one has a catalyst, and the red one does not. All right, so let's take a look at these. I couldn't decide how many hints to include, so I thought I did pretty good. I think I struck a balance. Where are you? There we are. Unit 2, Part 6. Okay, so your first problem looks like this, and what I've done basically is, I know there's a lot of words, but just take your time, read through it a couple of times. Notice that it says that it's observed second order NO and first order H2. That's what this means. The overall rate law, the observed rate law expression is this. NO squared, molar concentration, H2 raised to the first power. That's it. Okay. They go ahead and they give you information kind of like we've been talking about. They say there's 3 elementary steps, and the first one is fast, okay, and the second one, or the third one is also fast, so the slow one must be the in-between, huh? They tell you the fast one, they say go back in your textbook and look at equation 1425, so I brought it in here. So that means that the second one, in this case the middle one's slow. So, and I think this is where I kind of leave it. Basically, you need to fill in this gap with something that makes sense with, well, first off, you need to add these other 2 to it and get the reaction of interest. Okay, so kind of look at this product. This is actually going to be one of your reactants over here and proceed that way. Looks like an intermediate to me. And so it adds, this makes it so these 3 add up to get this, and also I think my hints were that that the molecularity of your slow steps 2 needs to actually give you that observed rate law expression. So there's that one. Play around with it. They take a little bit of time sometimes. So when it says show that it conforms to your experimental data, which is your observed rate law expression, this blue up here, do like we've been doing in class. And again, you will have to use that little trick that we just did for that last problem. The second problem looks like this. Okay, your reaction of interest is the H2 plus I2 goes to form 2HI. Okay, it goes ahead and tells you that the fast, it's got 2 steps. The first one is fast. It's equilibrium, I2 going to form 2I. They want you to, you're going to have to come up with the second elementary step. Of course, you have the reaction of interest. But your second elementary step needs to not only give you your overall reaction of interest, but also, since it's slow, it needs to ultimately shake out to be consistent with your rate law expression, observed rate law expression. Don't forget to prove your mechanism, like in class. The third of 4, reaction of interest, they're very similar to me. They go ahead and give you the observed rate law expression, second order for NO, first order for Cl2, okay? Two mechanisms, the first one's fast to equilibrium, the second one's slow. Of course, you know the reaction of interest. And so you're going to have to fill in the blanks. Try to see if they give you anything else. Don't forget to prove it. And last but not least, there is a typo. In so many semesters, I have not caught this. I don't know if they put an extra equal sign there. So actually, that should just be rate is equal to K times the molar concentration of O3 squared divided by the molar concentration of O2 raised to the first power. Okay. So of course, the reaction of interest is given above. They tell you it's first, there's two elementary steps. The first is fast to equilibrium. The second one is the rate determining step. Okay, so I think that's all I gave you there. Okay. Any questions? All right, just take your time. And they're not too bad, but they take some mulling over if you're like me.